Welcome to all of you. I'm Carsten Linnenberg and today we are in a biogas plant located in the city of Anröchte in North Rhine-Westphalia, Germany. The name of this biogas plant is Burger Gmbh and has a feedstock throughput of 140 tons per day or more than 51,000 tons per year. Since 2004, waste residues from the food industry, which is abundant in the region, ensure adequate electricity and heat production. The following videos are a description of the main units that make up the system for the generation of renewable energy and the treatment of waste residues to biofertilizer. About 140 tons of different organic wastes per day pass through this scale to control the material entering the plant and for substrate handling invoicing. This is the storage for solid substrates for the biogas plant. The principal feedstocks are animal byproducts such as stomach, intestinal contents, protein hydrolyzed, solid manure, meat residues with an approximately biogas capacity of 30 to 100 cubic meters per ton of fresh matter. Floats and sludge from wastewater treatment plants from the production of milk, food and beverage with an approximately biogas capacity of 60 to 160 cubic meters per ton of fresh matter, and vegetable products from the production of food, beverages and animal feed with an approximately biogas capacity of 130 to 200 cubic meters per ton fresh matter. In this hall we can find the storage of liquid substrates and the pre-treatment facility. The delivered residual materials are collected in a mixed storage tank from where the mixture is pumped through a macerator to guarantee a maximum particle size of 12 mm to the pasteurization tank. To ensure reliable sanitation without backmixing, the substrate is prepared in batches. Usually, pasteurization is performed without pressure at slightly above 70 degrees for 1 hour, achieved with an external heat exchanger. The pasteurized substrate is conducted in 2 digesters, where all the microbiology process of the system is done with mesophilic temperatures of around 40 degrees under anaerobic conditions. The substrate is biodegraded and transformed to methane-rich biogas by the presence of methanogenic bacteria. The heated digesters are insulated to maintain the right temperature and made of concrete. Here around 70 to 80% of the biogas is generated. The rest is produced in the post-digester and storage tanks of the digestate. In both processes, the biogas that was generated by anaerobic digestion is stored in the top of the tanks, which are sealed by a PVC-coated double membrane with an approximate total capacity of 10,000 cubic meters. In this double membrane system, the inner membrane provides the gas storage, whereas the outer membrane protects against weather conditions such as wind, rain and UV light. Air is blown between the 2 membranes to keep the outer foil stable in shape and wind resistant. All digesters, post-digesters and storage tanks are equipped with agitators to provide proper distribution of sludge and anaerobic bacteria within the tanks and to avoid sinking and floating layers. The produced biogas is guided in gas pipes in the CHP, combined heat and power, units through the slight overpressure in the double membrane gas storages. The biogas produced is water saturated and contains certain concentration of hydrogen sulfide, H2S, which is very corrosive and must therefore be reduced to a minimum before it is used in the CHP units. Consequently, the biogas is led through a gas cooler, like this, to condense the water vapor and pass through an activated carbon filter to reduce the hydrogen sulfide concentration to a minimum, before it is conducted to the CHP units. The biogas produced is converted into electricity in CHP units. Those plants convert around 35 to 45% of the energy contained in the biogas, which can be up to 6.5 kilowatt hours per cubic meter, into electricity, and 40 to 45% into thermal energy, so that the total efficiency of up to 90% can be achieved. In case more biogas is produced than can be stored and/or when the CHP units are maintained, the biogas produced is incinerated by an emergency gas flare to prevent methane from being released into the atmosphere. With the biogas produced at Burger Biogas plant, around 2 megawatt electricity can be produced constantly all over the year. The capacity of the CHPs installed are even higher to provide a certain buffer. The electricity produced is roughly equivalent to the demand of 5,000 households in Germany. The thermal energy produced at the same time is partly, around 30%, used to heat the anaerobic digesters and the pasteurization unit. The remaining thermal energy in form of hot water is stored by a 1,000 cubic meters buffer tank and is used as needed to provide heating to households in nearby village called Brillingsen, to some farmsteads in the vicinity of the biogas plant, and to dry the separated sludge. In addition to the significant savings expected for each household, the supply model makes a significant contribution to the energy transition. Extrapolated, the use of waste heat saves the energy equivalent of 180,000 liters of heating oil per year. The sludge anaerobically treated digestate is biologically stabilized and could be applied on farmland directly to substitute mineral fertilizer. No nutrients are lost during anaerobic digestion, so farmers can close the nutrient cycle and reuse the minerals. In addition to the nutrients, the sludge contains organic material which improves the soil condition and increases the organic content in the soil. Thus, the long-term application of digestate as fertilizer can increase the yield on the agricultural land concerned. On the other hand, the digestate contains a lot of water rich in nutrients. Farmers and/or biogas plant designers must have in account not to overload the arable soil with nutrients. For example, here in Europe, a maximum of 170 kilograms of total nitrogen per hectare of utilized land may be applied on average from farm animal manure and/or digestate origin, according to the European Union standards. Therefore, it is recommended that the volume of digestate is reduced by conditioning beforehand. In this manner, press screw separator and dryer systems were installed to reduce the amount of water from the digestate. The remaining liquid digestate is given to farmers near the biogas plant for direct application as liquid organic fertilizer, while the solid digestate can be even transported over longer distances with lower cost. Lastly, here we are in the control system, which is operated by a SCADA or supervisory control and data acquisition system, whereby the operational team is able to monitor and control the issuing of process commands, like for example controller set points, changes, times, pressures, volumes, levels, energy produced and other operational parameters. Well, this is the end of the presentation. Thanks a lot for your attention and we will see you next time.